Hello, everybody. Hello, TV listeners. This is Carrie Sundra from Alpenglow Industries, and this is the Wednesday solder sesh. We're not soldering today. That's okay. What we're doing today is some Kicad. Kicad or Kicad, Kicad, is an electronics program that, here, let me make me big. Why don't we do that? I'm now in control of the cameras. Robin usually does this, so I'm going to be worse at it. I'm going to forget that I'm... Why isn't it working? It doesn't like me. Oh, weird. I don't know. Here, we'll do that. Hey, I'm big now. Okay, so Kicad is it's a CAD program, a piece of computer software that is open source, and it is what a lot of people who are doing designs, electronics designs in the open source community use to design circuit boards, because that way you can easily share your circuit board files. Other people can take parts of your schematic or parts of your layout, which when you're open sourcing something, that's like part of the whole thing, is like part of the point is sharing, right? And enabling other people to like do things with your design. And so since it is a free tool, yeah, exactly. Kicad or Kicad. Since it's a free tool, it's a lot more friendly than the other tools out there, which range from, like at least 8,000, maybe it's up to 10,000 now for Altium for a seat, plus $2,000 a year, which is really expensive, and doesn't make sense unless you are actively working in the industry and generating yearly income off of that. And then there are other options like Eagle, which is now bundled with Fusion, and it's becoming like a little more pay to play. It used to have some free things, but I think that has pretty much all but ended. So anyway, Kicad is basically the option that everybody is using for open source stuff. And as you might have gotten because of the the way I'm saying things and the chat, is it Kicad? Is it Kicad? No one knows. Everybody will argue. I tend to say Kicad because that is how I first heard it in my head when I read it. And so that's kind of what I've stuck with. Although I believe that Kicad is actually kind of more prevalent. At least it seems to me that more people that I talk to say Kicad rather than Kicad. So I'm sorry if I give you all like that cringy, like, just saying it, that sounds so weird thing, but I'm probably going to keep calling it Kicad. Thank you, Mark. That's helpful. Mark says I pronounce it, and then he just like typed it out without any kind of phonetics. And yeah, like I will kind of go back and forth. And if I'm talking to somebody and they're saying Kicad, I'll kind of like mimic them. But since you are at my mercy in the live stream and I'm not audibly talking to you guys, I get to say it how I want, and maybe brainwash all of you into saying Kicad. Whoa. So just like I pronounce it, I say GIF. I'm sorry, but GIF, I know it's supposedly GIF, but it just sounds wrong. That should be, I don't know. Should be with a J, is my opinion. We'll leave it at that. All right, so enough about how the hell do you pronounce this word. Let's talk about what we're doing. So I am going to, boom, put this up there. So this is what we're working on. You can see the angry ghost of RBG there, looking at you, Texas lawmakers. She doesn't like that bullshit. So, I actually started work on this board. Let's see if I can actually kind of like share. Can I do that? Let's see. Here we go. Okay. So I started work on this board last year, right after she passed away. And it was, you know, it was kind of one of those things where like I had a lot of pent up angst about that. And so, you know, I decided to create something. And I took this, you know, it's like modeled off of the notorious RBG graphic, and which itself is mostly uses a public domain photograph of her from, you know, one of the Supreme Court like bench photographs. And so what I did was I did a lot of image manipulation in order to kind of get it in that form, because so I am used to using Altium because I actually do have a seat of that very expensive software, because I have made my living off of doing design work for people for many years. And, you know, in industry, that's what you do. And so it made sense for me at the time. But I mean, basically, I just stopped paying the 2,000 year maintenance this year because I like wasn't really doing much of that work this year, because I'm focusing more on like building up open source stuff, because it's just, it's happier, and I'd rather encourage other people to get into electronics. So so I'm in the process of, you know, I've 20 years of working with Altium. I'm in the process of learning Kicad. And, you know, with any new tool, it's of course like a learning curve, and I feel like I'm all thumbs and don't know what I'm doing and stuff like that. So so this board that you're looking at was entirely designed in Altium, and Altium actually has a worse image handling than Kicad. Kicad actually has like a very nice image import tool. So I had to do a lot of like crazy stuff in order to even get it into Altium. And you know, it looks a little pixelated because, you know, it had to be like bitmapped and hand jammed and all of this stuff. And then so her face, the white is all silk screen. So it's all like this epoxy ink that's layered on top of the circuit board. The gold, what you're seeing is bare copper, and it's been gold plated over top of that, which is a very common finish for circuit boards. And yeah, so Mark says those eyes are creepy as fuck. Yes, they are. And that's one of the things that I need to change, because like I didn't really intend for her to be that creepy and dead and soulless. But, you know, she does have a good, like, very angry zombie. I'm going to kind of look to her, which I think is appropriate right now. So, yeah. Anyway, so basically what she's made up of, and yeah, we have like, you know, some blurbles from manufacturing and stuff. Like, basically what you're looking at is just purple solder mask, which is over most of the copper on the board to protect it and to keep anything from shorting out. You're seeing white silkscreen, which is usually used for component markings that makes up her face in the main part of the graphics. And then the gold is exposed copper that's been gold plated over. And you can see like there are a few issues with this design, right? It is not the most beautiful thing in the world. Eyes are kind of soulless and creepy as fuck. What I should have done was I should have made her pupils dark, right? And just have a ring of what is that? Cornea? Iris? No, iris? Okay, around the pupil. You know, that should be the colorful part, and her pupils should be dark, and then she'll, I think, look a little more lively, hopefully. And then also, so you will see her face looks a little pockmarked, and that's because there are what's called vias, and vias connect two layers of a circuit board together. They're a way of putting a trace that starts on one layer and bringing it to the bottom layer of the circuit board. So this is a 2-layer circuit board. So it has copper on the top and copper on the bottom, and there's fiberglass in between. And so when you have a trace, when you need to like kind of jump over something but not touch it, you can jump down to the next layer on the circuit board. And how this is done is a hole is drilled in the circuit board, and it's entirely plated through. So your trace, you know, goes along, electrons go along, and then they get to this hole that's plated through, and they like go through the circuit board to the other side, and then the trace picks up on the other side. Your electrons still motor along. So Yes. So that's what's happening. There are vias there, and what you're seeing are the holes basically in the vias. And so what we can do is I can make those holes a lot smaller so that the silk screen and solder mask will just like completely cover them, and they will basically be invisible. So that is something I will be improving upon on the next revision. And so actually, Mark, for the eyes, that's actually what we're doing. So the eyes are, you can see like, well, how are the eyes changing color? There's not an LED component on the top of the board, right? You don't see anything there. Well, what's happening is the LEDs are on the back of the board, and they're actually side-mounted LEDs. And you're seeing the color through the board. I'm basically using that middle layer of fiberglass as a diffuser. So there's no copper on either side of the board in that spot. That's all been etched away. There's no solder mask, none of the purple that's covering that on either side of the board. And there's no silkscreen, no white on either side of the board over that. So you basically just have this like semi-transparent fiberglass that you're seeing the LED through, and that acts as a diffuser. So yeah, I'm still going to do that on the next version of the board, and do the backlighting thing, because I think that that's kind of cool. So what else is going on with this board? So this board has some bodge wires, because this is the first rev. So this board is powered. So they're normal RGB LEDs. They're not the addressable kind. I can't just like tell them to be a color. You actually have to, give the right voltage on the red, the green, and the blue lines in order to mix them and create the color that you want. And I am doing this with a At-Tiny4 processor. Oh, no, that's not the cue. Where are we? Right, we're in the middle there, right there. And so I know they're all SOT 23.6 packages. That's just what the name of this size of component is called. And there are transistors that are actually essentially turning the power on and off to each LED color. And the processor is the tiny chip in the middle right there. It's an At-Tiny4. And it's the one that is running the code, that is driving all that is cycling the colors in the proper order to kind of get this rainbow fading. And like that is actually like a whole nother topic that I think like that I want to do a blog post or something on, because like how to rainbow fade LEDs and what the PWMs look like and stuff like that, I think is kind of cool. Yeah, I don't want to get too far down that rabbit hole, because then we'll never get to Kicad. So yeah. So we got like some transistors that are controlling the power on and off to the LEDs. We have the processor that's controlling the transistors, which are just, basically like little electronic switches. We have a little coin cell battery that's powering the whole thing. We have some switches for on and off, and the one that I added for programming. And the other switch was supposed to be a mode switch that switched between this rainbow fading or just like red pulsing. That is not enabled on this one. And then down here, we have the programming header. So the other thing that's kind of interesting so the At-Tiny4, a little bit about that. It is my it's kind of like a favorite chip of mine, because it's like so tiny and wussy. It has 512 bytes of flash and 32 bytes of RAM. And that's bytes, not kilobytes, not megabytes, bytes. So it has what that means is it has like very, very little memory, like practically no memory at all. So your program has to be like very, very, very simple and efficient in order to actually be able to be stored and run on this tiny little processor. Like, why would you ever use a processor like that? Well, I'm kind of like, well, why not? like I can think of a lot of different things, especially like if you wanted to do like little earrings or wearables or something like that, where space might be at a premium, where you want like a really tiny processor. It also, like it's still cheap, but a year ago it was even cheaper, of course. It was like 27 cents in quantity, which is like ridiculously cheap for a processor. So if you have something that you want to control that is going to be like that, like, yes, I could maybe do it without a processor. I could maybe like put together a whole discrete circuit made out of a 555 timer and blah, 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 right? But 555 timers are actually, compared to this, they're relatively big chips. Even the smallest ones are. The smallest 555 timer is about 4 times the size, at least, of this chip. And it requires a bunch of external circuitry to work. So if you're trying to do something really simple, small space, doesn't have a lot of room for external circuitry, I think that and you want it to be relatively like pretty cheap, I think that it's kind of a cool option. And it's also like a super interesting challenge. Like, can I make code that does something cool that fits in this super tiny processor? And the answer is yes, I can. So we'll go now to the dev board. We'll zoom out because the dev board's kind of bigger. We just changed our setup a little bit, and so things are kind of higher and not as easy to get to, but it's better. So this is the dev board. If I can zoom in a little bit more. It kind of looks like a spaghetti disaster, like most breadboards should. And so what you see going on here is same at-tiny4 processor, that's that guy. And you see I have separated out the red and the blue and the green components into like their separate LEDs, as well as like up here, which is a little hard to see because it's the logo. There we go. As well as hooked it up to an actual RGB LED so that you can see how those colors actually mix and look together. But this is just the cycle that it's going through. So it's like, you know, ramping up red, decreasing blue, then ramping up green, decreasing red, and all the way around. And then this one also does have the mode switch, which I hope works. Maybe it might have to end its current cycle there. Didn't seem to work. Is that the mode switch? Oh no, that's the programming switch. Haha, never mind. Oh, that's the mode switch. So yes, now basically, you know, it just pulses red, so you get angry RBG eyes. Angry. She's very angry right now. Okay. So, and then you switch the mode and then it goes back to the rainbow pulsing. Yeah, so like 27 cents US for an @tiny. Yeah, Bob is saying that. Yeah, it is very inexpensive. And even now they're only 33 cents. Only like an increase of like 25% in the last year. Anyway, yeah, but oh, thank you. Yes. So this program that you see running in this @tiny4 takes up 512 bytes of 512 bytes. Thank you very much. Not a byte wasted. Although it's funny, like I'm sure there's somebody I follow on Twitter. Shoot, I forget his Twitter handle, but I will look it up and tell you. But like his name is Larry, and he does like efficient code optimization for a living, and I'm sure he could like probably reduce that down to like half of what it is or something. And also I'm not using assembly, I'm using C, and so if I had some assembly chops, I could probably even make that more efficient, likely. And that's kind of something that I want to do later with this, is like after this is kind of done and out there and into the world, I kind of want to revisit it, but code it in assembly and see what the difference is. So, yeah, that is the project that we are now. So we now have like a working breadboard here, which is awesome. And now we're putting that into Kicad in order to get a new revision of the actual circuit board made. Okay. So I have done a lot. Yes, fast code are us. Thank you, Brent. That is Larry's Twitter handle. Totally worth following. He does very interesting stuff. I got to see, he did like a presentation at one of the All Hands Active. They do monthly Zoom like show and tell maker meetups. Definitely worth going to if you have not been to one of those before. They're always super interesting. There's like a little part at the beginning where everybody gets to say a little bit about themselves and what they're doing, and then they have like a presenter or several presenters that typically go for like an hour or so. So anyway, he gave a talk at one of those that was like completely fascinating about code optimization, which I know it sounds like a super dry subject, like, oh God, like, kill me now, right? But it's like, it was really interesting seeing like how he could shave stuff. And also, I hadn't really thought about this until he started talking about it, but just in terms of energy usage, like how much energy is wasted worldwide by inefficient code. And that is something to really consider. So if you write efficient code, you are also contributing to saving the planet from climate change. So yeah, it was more than just tricks like, yeah, like shift to multiply, divide by 2. Like that stuff I'm kind of, I'm already pretty well versed in, and like direct register access and stuff like that. But yeah, it was like, I wish I could speak better about it, but yeah, it was like, it was really fascinating, the things that he was talking about. Okay, so Kicad, let's get another. Ooh, there we go. Get that up there. Maybe I'll just keep it there. If you have trouble seeing, let me know. I'm going to zoom in from this right now because I think that this is probably pretty tiny on your screen. So I'll zoom in and then like shift around the schematic so that hopefully you can see it a little bit better. But let me know if it still doesn't look good. So we'll start up here in this corner. So this is our @tiny4 processor. And this is actually a slightly modified schematic symbol because the default schematic symbol, it was nice that Kicad like had one already in its library. That is one thing I will say, like the libraries of like useful stuff are already very, very good in Kicad. This might take a little while because I was doing the work on another computer, and so I just installed Kicad on this computer, so it might be like loading some stuff for the first time. But and you can super easily search among all the libraries too, which is nice. So it already had like this @tiny4 symbol, and so, but you can see, so this is a very typical way of drawing schematic symbols for processors, where you don't do a direct representation of the pin pattern in the schematic symbol. You draw the schematic symbol for electrical signal clarity. That's all what schematics are about. They so if I don't know if there's anybody interesting or listening, maybe Brittany, we talked yesterday, maybe she is looking. If so, please say hi. But anyway, if you're not familiar with electronics and how boards are made and stuff like that, there are 2 steps. One is the schematic, which is the like electrical flow diagram, basically, and that's drawn in symbols so that you can understand where the electrons are going, what they're powering, what things are doing in a very kind of like natural way once you learn the code. And then then there's the layout part where you're like, okay, well, this was my symbol representation of what's going on. Now we have the actual physical representation. We have all of the footprints for all of the parts where they'll eventually be soldered, basically. And I'm going to actually connect the dots and draw lines in copper from one part to another. But because you have the schematic information linked to it, you can see like, oh, this leg on this part needs to be connected to this leg on this part. And, it makes it a lot more easy, and there's error checking involved and all that sort of good stuff. So because of that, you have schematic symbols that will not look like what the component looks like in real life. And it's very common to draw schematic symbols with power at the top, ground on the bottom, and then like all the pins in their port order, like on one side or the other, or both sides if it's a really big component. So, you know, you can see here that we have like pin 1 here, pin 2's down here, pin 3's back up here. You know, it like makes no sense from a physical standpoint. But from an electrical standpoint, oh, power comes in at the top, ground's at the bottom, and all the inputs and the outputs are in order off to the side. That makes a lot of sense. But I'm picky and I didn't like it. So I will sometimes do a mix of like symbol representation and physical representation, because I do find that when you're troubleshooting things, it is very handy to have like some sort of an idea of the physical layout of a part by looking at the schematic. And because this is a circuit board with so few parts on it, it's like a relatively simple circuit board, you know, it doesn't add a whole ton of confusion to also make that part look somewhat like it does in real life, for some things. So I didn't like that footprint or that symbol, and so I took it and modified it and made this one. I still kept power at the top and ground at the bottom, but I put the other pins on the sides of the component that they actually are on, just to make it a little bit easier for myself when I'm getting it, soldering everything up for the first time, checking to make sure that everything's good, just to make that a little bit easier to like probe out. So I have, you know, pin 1 here, pin 2 would be in between 1 and 3 in real life. Then pin 3, pin 4, pin 5 would be right here, and pin 6. That just makes it like a little bit easier for me, I think. Decoupling capacitor here to smooth out the power. The pull-up resistor here is there is, so reset basically puts your processor into like dumb, I'm waiting for something mode. And so that's how you initiate programming for a processor, and it's how you reset the processor. And you do that by attaching this pin to ground. Most reset pins have like a little bit of internal circuitry that prevents like small blips from, you know, accidentally like triggering a false reset. And they generally also have like internal resistors that hold that pin. We call it pulling that pin high. So there's an internal resistor like this one that is internally like connecting this pin to your input power voltage to keep it high, so that you have to like really mean it in order to like pull it low and actually reset it. But they tend to be really like kind of like high values of resistors. So it's what's called a weak pull-up. So you can still, like if you have a noisy, you know, power supply or something like that, you can still sort of like get false reset triggers on this. So that's why I have this external one here. I found that I did need it for the breadboard design. And I actually also kind of like needed this capacitor here to kind of quiet stuff down as well. I think that there's a fair chance, like I don't think I'll need the capacitor at all on the actual board layout, but I'm thinking about keeping this one in because it's like, it's kind of handy to have it sometimes. So yeah. You know, people can always just like desolder it if they don't want it there. But yeah, I'm kind of thinking of taking this one out for the actual design. I could keep it in. I could keep that pattern in and just not populate it. If I don't need it, that's an option too. But I'm kind of thinking I don't need it, and I kind of don't want it there. I don't want to have the expense of an extra capacitor and stuff like that. So I'm going to delete it. Kicad is different in selecting from Altium, so I'm still getting used to this. You know, you can box select and delete, which is cool. You know, that's pretty normal. But when you just want to select one component, it's a little weird. Like a lot of programs, you think, okay, I just click it to select, and then maybe I'll right click and there will be properties and I can alter it. It's not quite the same way with Kicad. When you right click it, you kind of like, or when you, no, now it's not going to do it. Maybe it's, yeah, maybe I've been in like move mode a lot or something. Anyway, it like behaves differently than what I'm used to. And a lot of times if I selected something by clicking it in Kicad, it would automatically start moving it. And that was like kind of weird to me. So yeah, you know, I'm still getting used to everything. If I just hover over it and right click, I still get to like properties and all the things that you can do to edit it. So yeah, do I know about dragging from different directions? Yes, I do. That is still a relatively new thing, and I have decades of habits where it didn't matter what direction you selected things in. So what Mark is talking about is like the difference in selecting by dragging this way versus selecting by dragging that way. And a lot of times this style of selection will select everything that is completely encapsulated within the box and nothing else. So if you kind of drag over something that's half in the box, half out of the box, it won't select it. Whereas like dragging in this direction will select everything that the box touches, like in its entirety. So yeah, I'm still getting used to like having those options, frankly. And also I haven't found there to be a huge difference in Kicad because like, as you can see, like, even though that line is not completely encapsulated by my box, it's still selecting it that way and that way as well. So I'm still like trying to figure out exactly how all that stuff works. Yeah, everything. Yeah, exactly. But okay. So, Brittany is in. Yes, electronics Noob ahoy. Awesome. So interesting. So Mark's saying it only maybe works on components. Let's try that out. So I'm completely, let's see. I will not completely select the capacitor, but I will completely select the resistor. It just selected everything, even the capacitor that wasn't fully in the box. And yeah, same here. So, yeah, and then it's just started moving. So like that's, yeah, it's still causing me like a little bit of confusion. Maybe there's a setting that I have to enable for it to do that. I'm not sure. So anyway, like move it along. So we have the processor here, and that's what's controlling everything. An interesting thing about the At-Tiny 4 processors, the 4, 5, 9, and 10 are all a family. And for people who are used to Arduino Unos, they have they are based upon a different, more higher power processor. And it has like things that have Arduinos in them typically have this 6-pin programming connector. And there's like a specific programming protocol and pins that are used. So this basically ensures that like the first time you get a chip when it's completely blank and stupid and there's no code in it, like there is some method of getting code into the chip, right? So so each chip will have sort of this specific programming interface that has a bunch of like internal hardware that like does stuff and is already like, I guess, kind of like programmed or set up to accept programs. However, the programming interface, the programming protocol is different for At-Tiny 4, 5, 9, 10s than it is for AVRs, for the like Atmega 328P that is in the Arduino. And it's also different from other At-Tiny processors. At-Tiny 85s are used a lot in Arduinos, and they're like a 8-pin processor that is much more capable and has larger memory than this one. But like it's an even different process from those, protocol from those. It only takes 5 pins. So it connects. The AVRs have 6 pins. They have like an out pin and an in pin, so that there's a single direction data, two single direction data lines. And they also have a clock and reset and power and ground. So instead of having two single directional data lines, basically this has like one bidirectional data line, you know, meaning that data goes both ways on it. And there's some sort of protocol for like when like the device that's doing the programming, like when the controller gets to talk, and like when the receiving device like gets to talk. And so that is a difference. And also, you generally need some sort of like a little puck, a little piece of programming hardware. You know, you can call it like a dongle or a puck or whatever. Let's see, I'll show you on the little screen that like this is one of them. It's hooked up there. It basically is like just a little board that goes in between your computer and your processor that kind of like formats the USB data coming out of your computer into the right kind of data that talks to your processor, into like this TPI protocol, for instance. A lot of the open source programmer boards that are used for AVRs don't talk the TPI protocol. So USB ASP does, which is what this board is. However, you know, the USB ASP was open source. No, like the person who created it doesn't sell the hardware. So, you know, there are USB ASPs everywhere. Tons are made in China. They're available on Amazon, whatever. For whatever reason, all of them use an earlier version of the software. And it's like, it's kind of a funky conundrum, because the latest version of the software is from 2011. It is 10 years old, and yet it is not what comes pre-programmed in these guys. They might just have their own software, right? They might have written their own software. They might not have taken the open source, like kind of official stuff. And anyway, pretty much I bought several of them, and none of them natively talk TPI. So you actually have to program the programmer with the latest 10-year-old version of software first in order to get it to actually talk to the board, which is like kind of crazy. But yes, I will be writing up a blog post with all this, because it was a lot of, oh, bye, Mark, see ya. It was it was like definitely like a snipe hunt on the internet in order to get all of this information together. So that's how you use the USB ASP with it. If you have an old school original AVR ISP Mark II that was legitimately produced by Atmel, it will talk TPI natively out of the box. But they discontinued that programmer because, I don't know, it was too cheap and convenient. So now there are a whole bunch of Chinese knockoffs, and none of them talk TPI. So if you have an old original AVR ISP Mark II, which I happen to have because I'm cool, it will talk TPI. But wait, there's more. So many hours of my life were wasted. I started out using the AVR ISP Mark II because that's what I had. I didn't have a USB ASP at the time. And yes, veteran of snipe hunts. So I was using the AVR ISP Mark II to program it. I finally got that hooked up. It was working great. I use the USB ASP. I do everything that the internet says I should do, that upload the firmware, you know, update the firmware, all of this stuff, and it doesn't work. And it keeps not working. And I'm like pulling my hair out. And then like, finally, I was like, I don't know, something took me to a schematic of like how you hook up a, you know, USB ASP. And I realized that the pin that they were using for the bidirectional data was the opposite one of the one that the AVR ISP Mark II is using for the bidirectional data. So to our schematic here, this is why this mess is going on. So we have a program. This is a programming connector. And you will notice that TPI data is hooked up to both MISO and to MOSI. And those are the two bidirectional data lines. Yeah. So yeah, it's hooked up to both of them. One you can use for the AVR ISP Mark II, and one you can use for the USB ASP. and it's fine to connect them both. I've used both the programmers with them connected together. It doesn't seem to affect anything. There's one more difference between the genuine Atmel device, wait, there's more, and the USB ASP, and that is that the USB ASP provides power. The AVR ISP Mark II, you need to provide it power. And so, so basically the USB ASP, there will be 5 volts coming in on this line, and our little LED indicator will line up. That's what this is. This is an LED. This is just a little resistor that controls current going into the LED. So we'll have like just a normal blue LED like on the back of it probably, so that it won't, interfere with our color mixing beautiful eyes. And so for the USB ASP, it will provide the 5 volts that's needed to program it. For the AVR ISP Mark II, we're going to need to provide it 5 volts. So, I was thinking of putting a switch in there, but I'm actually thinking I think that a lot of people will not have this, the AVR ISP Mark II. It's been discontinued. The USB ASP is much more readily available and cheaper and stuff. So I think what I'll just do, I was thinking of putting a switch in. The switches are expensive and big. I think I might just put a solder jumper here. So there'll be 2 pads that'll be close together. If you have this type of programmer and you're going to use it, you just put a solder blob between those 2, and this V processor input will then be connected to this 5 volts, and you can put in your own voltage on the V processor line. So that brings us to what the hell is going on here? So a few things are going on here. I have this big switch. So this is one part that has basically 4 different lines in it that are all switched together with one switch stroke. So that's called a 4-pole dual throw switch. You have 4 lines that you're switching, and you have 2 positions that the switch can actually be in, 2 signals that it can switch between. So the reason for doing this is a few things. There are you basically have to use these pins multi-purposefully because there are so few pins. On a processor with more pins, it is generally good. It's generally good procedure to, if you don't need them, to just use your pins that go to your programmer. You use those pins exclusively for programming, and you don't hook up anything else to it because other external circuitry might affect the way that it programs, because those programming pins have to, communicate very quickly, which means that they're switching between 5 volts and ground very quickly. And if you have something like an LED hanging off of them that draws some current, then they might not be able to switch fast enough for the programming protocol, and you might get errors while you're trying to program your chip. And that's no good. So generally it's good practice to just, separate out those lines, leave them just for programming, and use all of the other pins for circuitry. Wow, when you only got 4 pins to choose from, and 1 is your reset pin, so you really can't use that for other circuitry. You sort of can with this chip. I can get into that later, but you don't want to accidentally be pulling your reset pin low and resetting your chip in the middle of its program, right? So that one generally is dedicated. So that leaves us 3 pins, right? And we need 2 of those for programming. So obviously they're going to be multi-purpose. So basically I hooked them up to a switch so that we can switch those lines so that they go to the programmer, or we can switch those lines so that they go to the rest of the circuit. So while we're programming them, they won't be connected to the rest of the circuit. The other interesting thing, I know so many interesting things about the ATtiny4, right? The other interesting thing is that, the ATtiny4, you can run it off of pretty low. I think 1.8 volts is the lowest it can go, all the way up to 5. And, we're running ours off of a 3-volt little coin cell battery. However, it needs 5 volts to be programmed. You can't program it off of a 3-volt supply. So you have to switch the voltage to the processor if you're going to run it off of a supply that's not 5 volts. So that's the other reason for having that switch there and having them all together so that you don't accidentally like short out your battery, you know, hook up your battery to like 5 volts when you're trying to program it. So that's what this switch bank is doing. It's just switching so that the lines are connected either to the programmer or to the rest of the circuit. What's the rest of the circuit, you say? Well, we have a few things going on. The idea for this board is that not only will it be this cool RBG badge, RBG RGB badge, but you can also use it for like as a little dev board for putting your own programs in this @tiny4 chip, and you could like hook this board up to a breadboard and have your own circuitry on the breadboard and like test things out. So this connector will basically go to a bunch of pads at the bottom. So they'll basically like go to what I have going on here, pads at the bottom, which you can choose to solder a header to, like I have here, and then you can like plug it straight into a breadboard, or you can have it like off of a cable or whatever. And then, but you know, because we also have like our own circuit on board, right? We don't want that to conflict with whatever you're breadboarding on your breadboard. So basically we have some switches here where we can connect or disconnect the processor to the rest of the circuit. And so let's see. So you can see I've kind of, you know, separated out this schematic here. Make this maybe a little bit bigger so maybe you can read it. I don't know if you're going to be able to read that or not. Let me know. I'm interested if like at what point this text becomes legible for you guys. You know, here we have half the schematic, we have the dev board circuitry, and then the other half of the schematic is the actual, you know, RBG, RGB circuitry. So that one, I think it's probably pretty obvious, but I'll explain the play on words. You know, we have Ruth Bader Ginsburg, RBG, and then we have the RGB LEDs that is the circuitry. So anyway, and I now get them completely confused all the time. Thank you, me. So these are the schematic symbols that represent the RBG LEDs. RGB LEDs, see, there we go. It's never going to be the same. So each of the RGB LEDs is actually a conglomeration of 3 LEDs, a red, a green, and a blue, because those are 3 colors that mix together to make all sorts of colors of light. And so 2 of these LEDs, each containing 3 LEDs, and the resistors are there just for controlling the current to them. You'll notice that they have what's called a common anode. So they're all tied together internally on their positive side. So that's why they're both hooked up directly to battery voltage on their positive side. And then we have our like little current limiting resistors. They're different values because each of the LEDs creates its own individual voltage when current flows through it. And so basically they need like differing amounts of current to create like kind of more or less the same amount of light. So the green and surprisingly, the green LED had a very high forward voltage, almost that of the blue LED, which was, you know, in the high 2s. So yeah, they both get very small resistors because, you know, they need like a little bit more current and don't have a lot of voltage for it to go across. And then the red LED has a lower forward voltage, so it gets a higher resistor to limit its current even more. So basically, more or less, there's the same current going through all of them. And you know, I might play with this once these boards come in a little bit, because even if the current's the same, the brightness of those 3 colors might be different. So you kind of want it, and the way that your eye perceives brightness of different colors is different. So basically, we might just play with those resistor values a little bit to just get it to look the way that we want once the boards come in. And then legible in theater mode, not full screen. Interesting. Okay. Yeah, I think it might be also just like streaming, you know, resolution basically. So, but yeah, I'll try to keep it big for you here. And we have tied the LEDs together, the red, the green, and the blue of LEDs together. It's probably a little bit more correct for them to each have their own resistor and to be tied together after the resistor. But my thought is that, and that accounts for just differences within the manufacturing batch of LEDs. Like if this red LED is just a little different from this red LED, then they might generate different voltages. They might have like a different voltage drop, and like they might kind of start to fight with each other a little bit. And honestly, like for this, it's probably not going to be a big deal. LEDs are pretty consistent these days. It's like, I'm not worried about it. I'd rather not have 3 extra parts that I have to like buy, you know, pay for assembly of as well. I mean, resistors themselves are like super duper cheap. So, I mean, they're almost free, but the assembly of placing that resistor on the board is not free. So that's actually what you're saving. And then these are 3 transistors that are just, you can think of them as electronic switches. So, you know, which a microcontroller can tell to be on or off, and they are switching the ground. So when it's off, the LED is not connected and it's not on. And when it's on, it is connected and it's on. And the way that we dim LEDs, do I want to get into this now? I don't know. I'll get into it a tiny bit for you, Brittany. There aren't tie lots for LED manufacturing batches, right? Like it's sort of the same thing, right? But even, you know, even within a die lot, you might get a little bit of variation. I mean, there are kind of the same thing. There are definitely batches. Components within a batch will be more consistent than batches that are made that are the same component like at a different time, because you know, the environment will just be like a little bit different. Maybe the raw materials are a little bit different. Who knows? You know, variables. But yeah, it's totally the same thing. So yeah, we have little transistor switches. Basically, the way that you can, when you only have on-off control of something, right? Like, how do you control like the level of being on off? How do you get it to appear at like half brightness if you only have like completely off or like completely on and full brightness? Well, you just cycle it super fast. You tell it to be on half the time, you tell it to be off half the time, and you do that like, you know, thousands of times per second, and your eye averages it for you. So that's how we dim LEDs. And, you know, by controlling the percentage of time that we tell it to be on or off, we can control the brightness. So, you know, let's just assume right now that everything's linear. It's not important for right now. But like if full brightness is full on and you know, off is off, then like for 50% brightness, you tell it to be on 50% of the time and off for 50% of the time. And you just like make a square wave that just toggles between them many, many times per second. To be like at a quarter brightness, it's 25% on and 75% off. And like, that's the way you do it. You just control the amount of time. So that's what we essentially do with the microprocessor. That's what this signal coming in here is going to be. Pull down resistor is just to make sure that when this is all disconnected from the rest of our circuit, that it actually stays off, because these gates are very, very sensitive. So, you know, when things are just lying around unpowered, they do what we call floating. They kind of pick up electrical energy just from the surrounding environment. And so, you know, it might cause some of the board to be a little charged and some of it to be like a little not charged. And so things can kind of, you know, do what we call float, and they can kind of be weird when they're not connected to anything. And since gates are pretty sensitive, it's helpful to make sure that they stay off when they are not connected to anything. So that's why we pull them to ground with this resistor here. So we just make them be at a known potential. All right, one more thing in this schematic is this is the mode switch to control red versus rainbow. So every now and then, so basically what comes out, I'm used to in other CAD programs being able to like grab the screen and move it. And with Kicad, you can't do that. So you have to like either use the bars here or use like shift scroll. And I'm still like really not used to that. So I apologize if I'm sometimes like a little fumbly at this. I'm still new to this tool. So here, what we have going on is we have the our three lines. We only have 3 pins on this processor that we can actually use. All 3 of them go through this switch to be our red, green, and blue control. And so every time there's sort of the cycle where, you know, red ramps up and blue ramps down, and then red ramps down and green ramps up, and that's how it does this rainbow fading. And there are sort of 3 parts to the cycle. So after each of those 3 parts, what it does is it turns this guy, right now it's attached to blue. On our setup here, it's attached to green. But it takes this pin, and instead of it being an output that goes and controls this blue line, it switches it to be an input, and it actually like essentially reads the voltage on that line. Although it's a digital input, so it can only tell if it's like at 0 volts or at high voltage, which is, you know, battery voltage, 3 volts. So if everything is like hooked up, and if this is in normal rainbow mode, then this switch here, I should probably zoom in. Then this switch here is connected to our transistor, and it's pulled low, so it'll read about 0 volts. But if our mode switch is in this position, up like it is right here, then it'll read high. And it'll be like, oh, I should just be in red mode. And it then only fades the red LED. And then it keeps checking and it keeps checking. And then when you put the switch back over here, then it goes back to ground. And it's like, oh, I'm in rainbow mode again. And then it cycles through the rainbow. So yeah, multiplexing a pin to be an output and an input. Crazy stuff. Right? It's like, and that's why the @tiny4s are this fun challenge, right? Because I didn't have an extra pin that I could use for that mode switch. So I had to actually make that output pin also be an input and figure out how to hook that up electrically so that it wouldn't like interfere with each other and things wouldn't blow up, you know? So yeah, it's, I don't know, fun challenge. Can you do it? Don't ask why, just ask, can you do it? So yeah, I think that is it. I wanted to go over, so I have like my little to-do list in this corner of the schematic. Can I multiplex the other 2 output pins? Yeah, I mean, I could. There would be no problems with that. Of course, I can't really do anything more with this code since I am using 512 out of 512 bytes. And there was a little shoehorning at the end to get all of that in. But yeah, I mean, you could totally multiplex the other 2 in like a similar way if you had enough space. So like maybe that's a cause for you to upgrade to the @tiny5, which has like double the amount of flash. Whoa, crazy. That gives you a whole like 1K, you know, 1024 bytes. So I know I'm super geek about this stuff, but I just kind of love it. Watch out, world. You may have a new toy. Yes. Yes. I want other people to do stupid, simple things with that tiny processors. So yeah, okay, so my to-do list is down here. I like keeping this while I'm doing a schematic. It helps me not forget details. So I just like put it right on the schematic where I'll see it. And oh, also, I would just like to, to point out this fantastic template that Robin put together. Look at that. I mean, it is like super official. It has our logo. It has our Instagram, Twitter, YouTube, Hackaday, and website, which every schematic should totally have. Make sure they know where to find you. Anyway, it looks awesome. Thank you so much for doing that. And yes, so to-do list. Okay, what do we got going on here? So 5-volt power jumper for programming. That's what I was talking about. I think I want to add like little solder blob so that you can actually, choose if you have that AVR ISP Mark II, then you can choose to give it power. And you can do that by like maybe blobbing these two lines together and putting some input power on this, V processor line on pin 2 that is, going to be on that header that you can solder in. So that's one thing. Change RGB LED symbol. Yes. So, and again, this is just like, it's just like schematic aesthetics, right? And everybody has their own personal preferences. So these are just my personal preferences. You don't have to have the same ones. It's cool. I prefer that LEDs look like this. I like the filled in diode. Why? I don't know. It's just what I'm used to. And it also differentiates it from the ground style that I prefer, which is the unfilled in triangle. So like, yeah, I just like that a little bit better. And I feel like the schematic symbol that came with Kicad here, it just looks messy. And I think it's super weird to have this line in the middle of your diode symbol. That's not a thing. That's not normal, at least in my world. And I don't know, they just kind of look gross. I would rather them be cleaner and not have this big box around them either. I think it's pretty obvious if you have like 1D designator by 3 things that are like in a different color and obviously grouped together. Like I feel like, oh, it's obvious that this is a single RGB LED and not like 3 individual discrete LEDs. So I just feel like the symbol, like it has a lot of visual clutter, especially if it's, if we're zoomed out. And it also bugs me that like the RGB is like sideways. This is a schematic. You're only going to be looking at it in one direction. I feel like your text should be in the, direction of reading. So yeah, so potentially change that symbol. And then let's see what else. Change resistor symbols. I might not do. I think I'm fine with them. I was thinking that they looked too skinny, but I think I'm just, I don't know. I think I had been looking at the schematic too long at that point, so I don't think I'm going to change that. I did change the capacitor symbol. The default one with Kicad, it's just super ugly. And again, I know this is probably minutia, but like, it's when you've been doing this for many years and you get used to things looking a certain way, it's very disorienting when they don't look that similar way. So, this, and I also do have a legitimate reason for it. So yeah, this is, let me place it. Oh, I guess we didn't do place part. We just went to the library. Hang on, place symbol on this sheet. Now we load stuff. Okay. So actually I can just use the filter for easy access. I can just do C. There we go. Okay. Now look at that. It's like, I mean, come on, dudes. This is like completely out of scale, right? Like, look at that compared to your default resistor. It's just like, I don't know. It's just kind of giant and ugly. And it's like super bolded. Like, why did they super bold that capacitor, right? Like, what is going on? I don't know. I just like looked at that and I was just like, nah, not on my schematic. So I took it and I modified it and I made it smaller. The other reason, legitimate reason for making this smaller is that a lot of times you might have like a row of capacitors together And it might be because you need capacitors of different values, or you might use 10 microfarad. You might, like, let's say you have a power converter and it needs to have 22 microfarads of capacitance hanging off of the end of it in order to like smooth out the noise of that power converter, right? And have like a nice stable output. But it's like a small board, and 22 microfarad capacitors are kind of more expensive, and you're just going to put two 10 microfarad capacitors together there, and that makes 20, and that's like close enough. So when you have like a bunch of them together, like I can squish in way more of these capacitors than I can these capacitors, like all like in a nice tidy row together. So, you know, yeah, it's terrible. Get rid of that. So at tiny 4, oh, okay. So the 4 and the 5. Thank you, Bob, for that that clarification. So yes, okay. Yes, all right. The at tiny 4 has 512 bytes. The at tiny 5 also has 512 bytes, but it has like an extra little feature in it, which is an A to D converter, which means it can actually read like an analog voltage, so a voltage that varies between 0 and 5 volts. That tiny 9 has 1024 bytes, and so does the at tiny 10. And again, the difference is whether they do or do not have an A to D converter. So yes, thank you. Good info. So yeah, simple nonsense. Take out the reset cap. Haha, I did that. Cross it off the list, maybe. Oh, hello. Oh, we're over here. Sorry, windows are on different screens. So took out the reset cap. Okay. Separate out battery switch. Think about modular processor. I think I have thought about modular processor and decided not to do it. I was thinking it might be kind of cool if you could actually swap this processor out without like unsoldering it. Because that way you could use this board, like you could easily swap in like a 4 or a 5 or a 9 or a 10, right? Otherwise, you're kind of like stuck with 4 unless you want to unsolder that and solder on another one. But frankly, I'm thinking like the people that are going to be interested in this aspect of the board are going to be more advanced people that are probably totally fine with unsoldering and resoldering a SOT236 part, which is small, but it's not impossible. And, you know, the parts themselves are cheap. So, you know, you don't have to worry about like necessarily like saving that processor when you remove it, right? You can just like solder blob the whole darn thing, wipe it off with your iron and like throw it in the trash, no big deal. Or you can save it, whatever. So yeah, I think I'm going to keep that as is. Otherwise it was like getting way too complicated. I was like, oh, you know, I could do like a little daughter board and like but then that's like another board that you have to make, connectors that you have to figure out. And it was just like, it was going to add cost and it was going to be less reliable. And so I was just like, I don't think so. So, okay, I thought about that. I decided not to do it. I mean, you can still populate yourself whichever processor you want on this board. It is swappable. It just takes soldering to do it. Separate out battery switch. Oh, change resistor symbols, not going to do it. Off the list. Oh, this list is like practically nothing now. Awesome. Switch is like taking care of itself. So separate out battery switch. So this is like probably the last thing that I was thinking about doing. And I think I will do it. I, put this is like a single part that is dip switches. So dip switches, dip stands for dual inline package. So it just means it has like two lines of legs. And dip switches are those little ones. They generally have a red background and they're like labeled like 1 through 4. And they have like little white slide switch actuators. And you usually have to like, do them with you have to actuate them with like a small screwdriver because they're tiny. And so, they're used for stuff like this to put things in different modes. But they're not really meant to be actuated a whole lot, right? They're meant to be actuated here and there. The problem with this is that I also put the battery voltage through it. And which is fine. Like, you do want to be able to connect or disconnect the battery. But, if somebody is using it as a badge, they're going to want to do that to turn it on and off, right? Like, that would essentially be the on-off switch. And having a dip style, like a dip switch, be an on-off switch is just a bad idea. It's small, it's hard to actuate, and they don't hold up as well as like normal bigger slide switches do. So what I think I'm going to do is make this into a bank of 3 dip switches instead of 4, and do an extra switch that's like a bigger one, like these mode switches, just for on-off. And so basically it will be like, like this. It will have like 3 switches on it. They might not be side, or they might be side. I don't know. We'll figure that out later. But yeah, so I'll do that right now. And
because this one you added after the fact.
Yeah, that one I added after the fact. The programming switch I added after the fact, yes. Because I didn't realize at the time that I laid out this board that I would need the programming switch, and then I realized I needed it to isolate the chip from the rest of the circuitry while I was programming it. Because I did not, as I said, I laid that board out in like a weekend and like very like fit of angst. And so I didn't realize that like it could only be programmed at 5 volts, and then I would need to switch that. And, anyway, so I think what I will do is place a new symbol, and I will filter on switch here. So there's already like a very large switch library, which is very cool in Kicad. And let's see. Sorry, I can't make that text any bigger for you guys. I know that's probably not going to come through very well. But we have a whole bunch of different, sizes of dip switches. So I'm just going to select the 3 in a row dip switch and put that there. And then delete that. Oh, clarify selection. We want the dip switch symbol, not our little vertical line graphic. And then we'll move that and put that within red, green, blue. Yep. And then I'm going to, let's see, G. Which one do I want to grab, the label or the wire? Which one will drag both of them with me? I know. I will select and then press G, which drags them both with me. So I will just move this up a little bit out of the way to make room for our separate switch. And I'll grab that one. Same thing, pressing G. G means drag. G is for drag, but I keep viewing it as grab. I think that works out a little bit better. And then what I'm going to do here is I'm just going to hover over this and press C, and that copies that component. So now I can just put this here and G, grab that again, drag it down, grab that little end there and drag it across. Let's see, I feel like I'm gonna drag this down again and drag that across. So what's happening now is that sort of like it's hard to say like what's going to be the default for a slide switch. It just depends upon how it comes from the manufacturer. It's not super important because we're going to like test these all out too. So we'll be actuating it before it even leaves the factory here, the Alpenglow factory. Ooh, and I'm also going to grab this and move it so it's in the middle. That might be a little confusing, but I think it'll be okay. So default will be that, that the battery here, this is our battery voltage coming in. Battery voltage will be connected to nothing. And then, so that's essentially off. And then in the other position, it will be connected to vProcessor. And vProcessor gets, so there are 2 ways of like connecting a signal line together in a CAD program. One is you give it a name, you give it a label, and then where you put that label elsewhere in your circuit, there's like an invisible connection there between the 2. So that's what I've done on the V processor line, because adding that extra line kind of like, it confused things a bit. It kind of jumped up the schematic, and schematic is all about easy signal flow. So we have V processor there, and we have V processor over here. And when it's, so right now it's showing the processor like in programming mode. When it's switched the other way, it'll be connected here to all of these processor lines, and it'll be in like normal run mode. And so our battery voltage will go to the processor. And then let's see. Oh, that's an extra one. We're going to delete that one. So cool. So we did that on our list. I want to try to add the little jumper there. Again, I could add a switch there, but it's like, we already have 3 switches. Like, do we really need a 4th for like a sort of side use case? Meh. So we're just going to do a solder jumper here, which the default will be that it's not connected, and then you'll just solder blob over it to connect it. And we're going to do that between the 5 volts and the V processor for this particular programmer. Oh, yeah. No, yes. Will that work? Hang on. I'm thinking about it. Yeah, so it'll work, but you will have to be careful to not be powering this board simultaneously, essentially. So it will take a little bit of user caution in that case, because if you're giving this board power on the V processor pin, if you're giving it 5 volts to program, and this guy is connected to your battery, then you're gonna like short the battery to 5 volts, and that'll be bad. Okay. So yeah, I mean, and I don't really want to put I could solve that with a diode here in line with the battery, but the battery is already so low voltage that I don't want there to be a diode drop in voltage as well, because that means that our board just wouldn't last very long at all. So I don't want to put an extra switch. I'm kind of like, if you're doing this level of stuff, then maybe you should know to be a little cautious. I'll just put the solder jumper in here for now and see how I feel about that. Yes, Bob, for a badge, side-mounted switches are definitely easier to access when worn on clothing. Correct. I agree. Doesn't my 4BDT? No, this guy does not really. It does not disconnect the battery really. Only this one disconnects the battery. So, so like, yeah, there's still a way of disconnecting the battery. You just want to make sure that you've done that, which can be easy to forget, right? So yeah. But yeah, so this does not disconnect the battery if they're jumpered, right? Because basically the only way of getting 5 volts into the board for a programmer that needs to be provided 5 volts is kind of through this connector right here. So it has to come in here and then be jumpered here, so it's on the opposite side of that switch. So that switch would not prevent that from happening. I'm just going to put it in, and I might do something different with it later. Who knows? But do replace symbol. I don't know actually if Kicad has a solder jumper. Let's see. Ooh. 2-pole closed bridge. So I also don't know which of these. That's looking like it. Oh, open. Yeah, that's what I want. So it's just a symbol style. Here, we'll see it in a second. This is a common one that people use when they indicate 2 pads on a circuit board that can be solder blobbed together in order to be jumpered. So I'm also going to go to properties here, and I don't want to show that big long description, the solder jumper to blah, 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 blah. So I'm going to hide that. I also think that this is funny. Like I am used to most programming's it being hide, not show. So it's kind of like the opposite of what I'm used to, but that's okay. So yeah, so then we will, I think Shift W puts you into wire mode. So now I can connect the dots. La la la. Sorry. I'm telling you, circuit board layout, it's just a grown-up game of connect the dots. That's all it is. Anybody can do it. So yeah, we'll put that there. Okay, cool. So we've done 2 out of that. I'm not going to change the RGB symbol right now. So now I think what we're ready to do is to what's called annotate the schematic. So you might notice that all of my little components, we have what's called the reference designator here. So R means this part is a resistor. D means this part is a diode. And J, for whatever reason, I think it actually stands for jack, but it's sort of an all-purpose thing that means connector these days. And the question mark by it is because we haven't had it number them yet. You usually do that at the end when you're not going to make many more changes to the schematic. And because that way the numbering tends to sort of be nicer and flow from like one part to another in a more intuitive way, but not always. It doesn't matter too much. So, and the number beneath it is just the value. So this is a 220 ohm resistor. This is a blue LED, that kind of a thing. So now I believe we have tools, annotate schematic, scope, entire schematic, orders. Do we want to go down first and then across, or do we want to go across first, then down? That is the eternal question of schematic annotation. In our case, I mean, I think it doesn't really matter. I'm going to say across first and then down because most of our signal flow kind of goes this way instead of that way. So let's go back here. So cross first, then down, we'll go by Y position. Option, it doesn't make any difference. We don't have existing annotations, so that choice doesn't matter. We'll just say reset just in case anyone actually did get one. Numbering, use first free number after 0. Cool. Let's do it. This will change the current annotation and cannot be undone. Ooh, cannot be undone. That's an interesting feature. Go ahead, do it. Annotation complete. Close. Yay, now we have numbers. Numbers are good. And because of the way that these transistors are on the schematic, they have gotten like nice logical numbers assigned, 1, 2, 3. So yeah, I think I'm good with that. These all got assigned 2, 3, 4. That's good. Like, I'm happy with that. Awesome. All right, I'm gonna save this too. Hey, save. Cool. So now the next thing I would do is do an error checking. Where is that here? Do we have? Okay, so usually I would perform an ERC, an electrical rules check. What that would do is check if I have any wires that aren't connected to anything that just like end in the middle of nowhere. It would also check if I've like set up rules about certain pins being inputs and outputs. I would make sure that like an input was connected to an output and like 2 outputs weren't connected together, that kind of thing. Let's see. I love it. We have somebody in the comments saying that they hate to draw schematics. They'd like to make circuit boards quickly. I know it is this thing where you're just like, I want to get to the fun stuff. I want to get to the layout, right? But like schematics are so important. And like, oh man, when you miss stuff in schematics, that leads to errors and that leads to boards not working and to you being very, very sad. And it's also worth taking some time to make sure that your schematic is like readable and relatively legible and like looks nice and has notes where it needs notes, that kind of thing. I totally understand that feeling, but I will also say, like, it's a bit like swatching for knitting. Like, I don't want to swatch. I don't want to knit this useless square that, just tells me about how many stitches I'm knitting at compared to what the pattern assumed. And if this garment that I'm going to spend several months and maybe hundreds of dollars of yarn knitting is actually going to turn out into, to be the right size. Same sort of thing with the schematic. Like, putting effort into the schematic ahead of time is like important for having a board that works at the outcome. Yeah. So let's see. Does my original RBG RGB board have multiple FETs and SOT23? Yes, it does, in fact. So yeah, it has the transistors are in the same packages as the same package size as the processor. And yeah, I used the packages where like two transistors were in one package. I decided not to do that this time because I have 3 transistors. So if I used the dual package ones, one would be not used. Also, the dual package ones, there are more variations to them because sometimes they'll have some pins connected internally or not. They are less readily available. There are fewer, and with like right now with the electronics parts shortage thing going on, like basically if I got into a place where like the dual transistor package in the configuration I needed in the size that I needed, like that could easily not be available. And whereas a typical like single transistor in a single package, like I'm using it's the same size package, essentially. It just has 3 pins instead of 6. And like that is going to be available by like many, many, many different manufacturers. And it will be no problem to substitute a different one in. So that's why I made that decision, was purely a sourcing perspective. Yeah. Brittany, swatching? Never. Yes, swatching. Well, almost always. Maybe not if you're making a shawl, but then you can't complain if you run out of yarn. Like, oh, right. It doesn't matter if the fit's not, if the shawl is bigger or smaller than it should be, but if it's bigger and I ran out of yarn in the middle of it, ooh. And what if it's hand-dyed yarn and doesn't have a dye lot? Yeah, been there. So yeah, schematics, good. So yeah, okay, so the electrical rules checking, I know that there's a way to do that. Do you know where it is, Robin? Footprint editor, annotate. Perform electrical rules check, the little ladybug. Look at that. All right. Okay, this is weird. Oh, wait, it hasn't run yet. Okay. So this is definitely different than what I'm used to. Okay, this is more like it. So there's usually this matrix. Sorry that it's probably not going to be super legible. I mean, I can make the whole window bigger, but it doesn't zoom. So I can basically control a little bit here if something is like a hard error and I will need to fix it before proceeding, or if something's like just a warning, or if something's like totally fine, yo. So yeah, there are a bunch of rules. It's already set up. There are a bunch of rules built in. I'm just going to run it right now and see what happens. We'll see what errors pop up and if they're actually important to this layout or not. Okay, pin connected to other pins but not driven by any pin. Pin connected to other pins but not driven by any pin. Pin not connected. Use a no connection flag. Okay, so some of the pins on our switches are not connected to anything. So I think I will actually use like a little X. It's a no connection flag. I have actually been bitten by that one. Like something that was supposed to be connected once was not. And so that's what this is checking for. So then I have four that are like pin connected to other pins, but not driven by any pin. Basically what that means is that a lot of these symbols, these symbols were pretty much all pre-built. I just like might have modified them a tiny bit. I tend to not do boards that are so incredibly complicated that you need to like check whether an input is connected to an output. And like a lot of times, like, you know, in this case, you might have a bidirectional pin, which you can also, you know, make bidirectional, but a lot of times it just doesn't matter all that much. And so that's one that I tend to let slide a lot, because for the simple-ish stuff that I'm doing, it's just like, yeah, they're all going to be inputs or outputs, and you know, I'm probably going to connect them right. And you know, some things don't even really have inputs or outputs, like, you know, your LEDs and stuff like that. They don't, you know, really have like an input pin and an output pin. So, and like resistors don't have an input pin or an output pin either. So, you know, if you're doing something more complex, then it might actually, you know, be helpful and be required. But I find in a lot of stuff that I do, it's just like, meh. All right, so let's put our no connects. So this switch is all connected. That's good. This one has, whoop, right there. Hey, look, a little arrow pointing to it. How helpful. It would be helpful if it was maybe slightly bigger or a different color. But, you know, once I zoomed in forever, I saw it. So I'm going to place what's called a no connect X. And then I'm going to like look around and see if there are any other places where I needed to do that. So on, off, mode, those are all connected. I think we're good there. Cool. And so now in my, where was it? Bug. It's funny that it's not under tools. That's just like, oh, it has its own thing. Inspect. Got it. All right. So, okay. So output pin error, no connections error, unspecified pin. Oh, warning. Oh, was it errors or warnings? Hey, oh, hang on. Sorry. Spazzing out. There we go. I can't really tell if this is pin connected to other pins but not driven by any pin. I feel like unspecified pins are all warnings. Power input pin, tri-state pin, bidirectional pin, power output pin. All right, well, I'm going to try to create a netlist and see if it barfs or not. I can't tell if that's, I mean, it says error list, but I can't tell, like, is that a hard error that it's giving me, or is it a warning? Does it even matter for Kicad? Who knows? Let's see. So now, next step is to generate a netlist. So that is just, it is literally a list of nets, connections, basically each of these individual lines, each of these lines on a circuit board that are all connected together are a net. And and so a lot of times we might see this when we go to the layout. When you initially import all of your components into your layout, they'll all be jumbled together, and you'll have these connection lines going between all these pads, and it is actually called a rat's nest, which I thought you would kind of enjoy. So I haven't attached footprints yet to any of these. I don't know if, I'm guessing that, yeah, that's probably going to be part of my net list. So let's attach, it didn't do an error, but let's see about attaching footprints maybe. That is a separate, there we go, assign PCB footprints to schematic symbols. So now we're, okay, I must configure the blah, 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 blah. This is the first time I've run this part of Kicad. So, okay, I must first configure the library table to include all footprint libraries not included with Kicad. Okay, maybe we won't do that right now. Or maybe it's doing that right now. Oh, yeah, it's loading footprint libraries. Hang on, can't drag this yet. There we go. So it is loading footprints. We shall wait. and drink more beer while it's loading footprints. Level line, pale ale, 5%, so that hopefully I don't get too tongue-tied. Bob says, as an alternate, could I use 2-pole dual throw switch to combine the power and LED mode? Yeah, less components, but probably a higher price. So yeah, so basically that kind of switch would be like would be a switch kind of like this, but it would only be half of it, right? So these two lines would both toggle with the movement of a single switch. Yeah, but that wouldn't really work, because then if power was off, then it wouldn't matter what mode it was, and there would be only, because there's only in a 2-pole dual throw switch, there's still only one actuator. If you mean like combine two switch, like have two separate switches in one package, like a dual, it would be like a dual single pole dual throw, I think is what that would be called. That would potentially work. I haven't like looked at those and priced those out. I can get like little slide switches that are pretty cheap, that are single pole dual throw. So yeah, so I think I would do that. Okay, so let's see. We got footprints. We need to make this bigger. Ooh, a lot of information being conveyed. Okay. I haven't used this part yet, so this is new learning for me. So, so first we have the battery. We need like the battery holder, and so I think that there should be a CR2032 footprint already available. I think somewhere. Oh yeah, look at that. So basically, like if I do this and I do CR2032, that's like your like most common coin cell battery. Oh, interesting. It didn't seem to actually filter anything. Okay. I have this filtered footprints section over here that's probably just filtering like maybe on battery or something. They're a bunch by Keystone. But they're just, 3 times AA. Oh, okay. One of those, some of those might be, there are 2 2032s. Can I get a preview here? It would very much help to see what I'm selecting. View selected footprint. Okay, excellent. So yeah, this is kind of what I'm thinking. We have this is actually a really good question. So, could you get one of the surface mount I voted boards? Mm-hmm. Cool. There should be one in that like little bin that's on the test bench. Yeah. Cool. Oh wait, actually, this one has it on it. Haha, never mind. I didn't even realize. Okay, so this guy can be a little problematic. Too much finger to focus on. Come on. Here we go. So this is like a pretty standard CR2032 battery holder. Battery just slides in from the front and it just, solders down on pads. Now, the key to this style of battery holder, the weird thing is that it's nickel plated and it's probably like, I don't know, like brass, I'm guessing, that's like stamped brass that's then nickel plated. The nickel plating means that you can actually solder to it. It won't like tarnish or oxidize if it's just sitting out. Yeah, so the nickel plating is supposed to mean that it's easy to solder to. But the reality is that, I don't know, this style of nickel plating, it just sucks to solder to it. It really, like, solder wetting out on it is a problem. And so we had a bunch of these surface mount I voted boards made, and they, it was normal reflow process, lead-free solder, which does not wet out as nicely as leaded. And we had a problem where just the pressure of having the battery in there, because they're little like spring-loaded contacts, it was like popping the holders off of the board. Like the solder joints were failing, and it was just like popping off at the solder joints. And so like we noticed this relatively quickly, but sadly, because we, shipped some out and had some customers that were unhappy with their thing falling off, which of course we like immediately replaced. But we had to basically go for every single one and frickin' hand solder both tabs on either side to the board, and basically just like drown it in solder and make sure it was completely encapsulated and stayed down. And like, that's a super pain in the ass. So I'm like looking at this board and I'm like, oh God, do I want to use the same battery holders again? And I'm like, we might run into the same problem. Like I feel like it wasn't necessarily like a bad board house thing. I think it's more just like that connector and lead-free solder just like don't mix very well. Although I'm using, so this board I'm going to use Cyber City circuits for, and David is super cool, and it is always nice to have a board house that is where you can actually contact technically knowledgeable people. And like, I could email him and be like, yo, David, I had this problem with this other board house. If I give you this style of connector, is this going to be a problem for you guys too? Because he's probably done some boards with that style of connector. And so he might be like, oh yeah, we have to like run that at a higher temperature or whatever, or for longer. Like he might've figured out like, oh, there's a way of processing this type of connector that makes that like solder joint fine and not a problem. And it's really helpful when you can actually like talk to a board house and ask them those questions. And that's, that's one problem with like the consolidator services, that it's hard to get answers like that. It's hard to talk to a human and like get that kind of specificity of information. So yeah, we might want to just use a different style too. But I think for right now, we'll just go with a pattern that's the same style, but know that that's a thing, and that we might change that before doing all of the like final layout stuff. So these are the two styles of Keystone ones. They're not quite what I'm looking for. Oh, that's pretty much what we're looking for. That's the style. Let's look at this guy. Oh, yeah, same kind of thing, but I like the artwork on this one more because it's more representative of the actual shape of the battery holder. Gives you an idea of like which side should be the open side where you can actually insert the battery from it. Oh yeah, add that concern to your to-do list. Good point, Bob. I will do that. All right, so I'm going to select that one. So battery is selected. That's selected. Apply, save, and continue.
I think you have to double click it.
Oh, okay. I was like, it didn't
ran into that.
Didn't populate it. Yep. Double click. Thank you. So actually, I'm going to click OK out of that. Add to the to-dos. Side on CR 2032 footprint. I will know what that means later. Okay. And back to footprint editor, or actually footprint assigner. So it's nice that Kicad has all of these footprints that are already built in and easily accessible. I think most of the CAD programs kind of do have libraries available now, but you still end up making a fair number of footprints on your own, which, depending upon the CAD tool you use, can be like, not too bad, or a total pain in the ass. I don't know what Kicad is yet because I haven't done it. So for capacitors, we are going to use, weird, like this filtered footprints thing is kind of throwing me. Oh, there we go. Capacitor SMD. Okay, the filtered footprints is going on my selection over here. So I know that I want to use a 603 size. Interesting. Capacitor, because that's what I like to use on this size of thing. Oh, interesting. They have like a hand solder footprint, so it probably has like slightly bigger pads, or they have sort of like a normal size footprint, like probably like a little bit smaller for like machine pick and placing. Now, even though I do intend on having, you know, this one made out of house and machine pick and placed, I think I'm still going to go with the hand solder size pads just so that it's more easily reworkable, so that it's more easy to probe stuff. You know, dev boards, it's nice to be able to sometimes replace components if you need to. So we'll do that for that. Now, let's see. And the resistors are also going to be 603s. I'm guessing that they probably actually have a different resistor 603 pattern, which some people do. I use the same footprint for resistors and capacitors because I'm just that way. I don't find it to be very different. So interesting. I feel like this is a little bit smaller than the capacitor one. Maybe. We'll see. All right. Resistor footprints. Let's see. Will it do? Yeah, it'll do all of them. Excellent. So now we have our transistors. So we'll see about transistor footprints. And transformer. I don't want to. What would it be under? SOT. Package. There we go. Package SOT SMD. And if you have any trouble telling your SOTs apart, Alpenglow Industries sells a fantastic tool called the What the SOT Ruler, which is perfect for this kind of purpose. Now with the break from our sponsors. Okay, so I'm going to look for a SOT 23 because that's the package size that I need for these transistors. Ooh, is it going to be the SC number or the SOT number? SOT number. Yeah, that's interesting. Okay. Do we have a hand soldering option to that one? Oh, interesting. That's the fat one. Oh, there we go. SOT 23 hand soldering. Oh, that's big long pads on that one. Sure, why not? Okay. Oh, whoops. I didn't mean to exit out there. Hello. Let's see. Thank you, Bob. Alpenglow Industries rules. I love it. I feel like we need t-shirts that say that. Okay, I'm gonna redo this because I accidentally quit and I clicked OK thinking it would assign it, and yeah, that's not how it works. Okay, so it was in package, SOT, surface mount, and it was SOT 23 hand soldering. Double click. There we go. Okay. And this will be an interesting one. Well, these will be all interesting ones. Okay, so our normal LED that we're just using to indicate whether there's power from the programmer or not, that is going to be also a 603 package, but it has to be, it's directional, so it has to have one pad that's marked so that you can match that up to the marking on the actual LED and make sure it's populated in the correct direction. So I'm hoping that maybe there's a diode surface mount. Excellent. Yes, 0603. There we go. Hand solder. Let's look at our thing. Oh, man. God, I hate that footprint. I'm going to have to change some of this stuff. I won't do it right now. I'll do it later. But interesting. boy, that is a weird way of doing it. So, yeah. What I'm seeing here is that I think this blue is what's going to be actually printed on the circuit board. Generally, you just print one line and it's on one side or the other to indicate like what pad needs to be matched up to the pad with the dot or the line or whatever on the actual component. And this is really weird that they're sort of like trapping half of it. They're kind of like, I feel like it's a really big marking, and I feel like since it all is close to both pads, it could potentially be confused. So I would just make this be one line in front of pin 1 essentially, and that's what I'll probably do, because that is more normal for me. Like that's kind of a little bit weird. So there we go. And so the RGB LEDs are this interesting package called a 1204, which might not be in here. And they have 4, RGB LEDs have 4 pads instead of a normal 2 pads for diodes, because they have red, green, blue, and ground, or in our case, positive voltage. So I am not necessarily seeing like a multicolor. Look at this. There's a different library for LEDs versus diodes. So actually, maybe we'll go back to this one and let's look at the LED footprint. And I think it's like the same. It's sort of the same. Okay, but maybe this will have like an RGB one that we're looking for. Oh, RGB. LED RGBs. This is 1210. Oh yeah, that's not at all the same. Ours is also, it's like a 1204, I think, is also like a specific one. A 1204 LED pattern, I think, is a specific one to RGB side mount ones even, perhaps. So I'm just going to kind of go through these RGB ones and see if any of them are at all similar to what we need. And like, oh boy, howdy, the answer is like new, 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 and new. I'm just gonna like kind of, that's a side mount. It only has 3 pins though, so not useful. Oh, look at that. King Bright, blah, 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 blah. That actually might be right. Let's see. This is why it's very helpful to be able to have like an easy way to like just cycle through patterns, because your brain is like way faster at identifying if it's right or not than like reading something and trying to figure out what the hell it is. Brains, they're great things. Great and wondrous. Yeah, these are going to be all the 2-pin ones. Ooh, no, that's weird. Okay, so I think the best one that we saw so far was that King Bright one. I am going to put a note in, though, to double check. So when you go from schematic to PCB and you assign all of your footprints, and I know we're getting late and we're not actually going to get to the fun part of connecting the dots in the PCB this time. Stay tuned for next week, folks. But the first thing you want to do before even you place your components on a circuit board is like, you want to do that import so that you see all of the footprints for all of your components, and you want to print that out 1-to-1 on your printer. And then that is like the most important sanity check that you can do for any circuit board, because a lot of times you'll even think like, you'll have the right number of pads and stuff. You'll be like, oh yeah, this is totally the footprint I need. And then it'll turn out like when you get the boards that you're like, oh God, that was like twice the size that I needed, or half the size that I needed. It's completely the wrong size, even though it has the right number of pads. And like on a screen, you just don't have enough context because you're always looking at everything so zoomed in because, you know, these components are all tiny. Like you just don't have a good idea of what actual scale is when you're designing a circuit board on the computer. So always super important to just like print it out and like take an actual component with tweezers and put it on there and check it. And this is also where having some sort of magnification, a microscope, even like a USB microscope, even like a cell phone camera that you can like take a picture and zoom way in on. Those are all super handy for footprint checking. Totally the most important thing you can do. That's probably the swatching of circuit boards if I were to compare it with knitting, for sure. All right, so we're going to select these two LEDs and make them that footprint. And before I forget, we're going to go back here and we're going to say, check. I mean, we'll check our footprints anyway, but just to like double, triple check the RGB side mount footprint. Cool. All right, back to footprint assigning. What I'm going to try to do is get to the point where we like hopefully just like can import them, at least see them all on the screen, because that would be cool. And then we'll call it a night for the night. Okay, so we have, this is going to be interesting. I don't know if they're going to have this. I would imagine that they would have this standard programming connector for Arduinos. Let's see, view. It's kind of annoying that the view doesn't automatically pop up. Like I feel like, ooh, there it is. Look at that. That's a through-hole version though. That's a through-hole version too. They might not have a surface mount version, huh? We of course need a surface mount version because we can't have through-holes on this board because it would mess up our lovely graphics. So everything has to be on one layer on the backside and all has to be surface mount, so that nothing pokes through. They do not appear to have it under IDC connectors, which is the style of connector that it is. I'm wondering if there's like an Arduino library or like an ISP. ISP stands for in-circuit serial programming. And I don't, what is this? Filter footprint is using a partial name or pattern. Okay, maybe I have to do that. And then, is it only looking in that pattern? Yeah, it might only be looking in the library that's selected. So what if I go in normal connector library? Oh, that's interesting. No, I'm not really seeing what I need. Oh, this is interesting. This is almost it. Tag Connect. This is like a it's a specific style. It's a very compact spring probe like device that is used for programming Arduinos like in kind of semi-production environments, because the spring probes take up very, very little room. They're smaller than like the normal connector there, and you can just like press them down to the board, click program, and have it program your board that way, and then just like take it off, go to the next one. So you don't have like the wear and tear or the cost of putting an actual connector on your board. You just need like pads that the spring contacts come into contact with. So it's interesting. It's like sort of similar, but not really what we need. I wonder if there's an SMD connector library. No. Connector pin? I don't think so. No, that's just like single pins. There are some for specific manufacturers here. I do know that Worth has that style of connector, so I'm gonna, since there are only a few connectors in the library, not at all what we need. Also interesting that they spell Worth with the E, because I don't think it has one. let's see. I know T connectivity has that style of connector. 1 by 3, 2. It's definitely not like a mate and lock series. No. Okay. Yeah, I feel like we're going to have to probably, so these are all Samtech surface mount ones, but I think they're all like kind of standard, 10th inch or 10th inch or less spacing kind of. Well, this is a standard 10th inch header that is a surface mount version of it. But let's see. Let's look at, no, 106. What about 103? Oh, this? One of these might actually work. They do have like holes in the middle of them. But I mean, honestly, like I think I would just want to make my own, because the other thing is I want to make sure that the silkscreen outline is big enough to encompass the actual connector, because basically if I make my silkscreen smaller than the actual connector, then I might forget to leave enough room around my component and I might encroach other components on it. And then you'll go to like put that connector on and there will be other components in the way. And that's no good. So I like to make my silkscreens actually representative of the space that the connector or the component takes up on the board. So yeah, I will look for that later. I hope that it'll allow me to import with something unassigned. I don't know if it will or not. Boy, it's going to be sort of the same for the breakout connector, because I'm not using typical through-hole connectors for this, which is kind of what they have a lot of. And connectors, by the way, they're by far the most individual components. They have the most variety of footprints, the least standardization. So yeah, that's just, it's not uncommon to have to make your own connectors or to make your own specialized components at all. So the solder jumper, let's look at that. Solder jumper. Let's see, those are bridged. We want open pads, rounded pad. Ooh, triangle pad. Oh yeah, those triangle pads are kind of slick. I think we're going to do that one. Let's see, connectors we're leaving, and we got switches. Yes, so that's a good point. Bob says if I have the RGB LED component selected, if I know what supplier I'm going with, then there are suppliers that are actually now supplying Kicad libraries for their parts. That is always helpful. And yes, so you might not have to create it all on your own. Like a first good thing to do is always to check and see if it's already available on the internet. And other people also might have made libraries. It's kind of like, sharing like 3D printing models, right? People put libraries up all the time, also for circuit board components and layouts. So you could totally search around. But also, like, I have no problem like creating my own using an editor that's like, because the editor is like built in here to Kicad. So, getting familiar with that tool would be good for me too, because I haven't used it before. Okay, so we're on switches. Bitches. Ooh, interesting. I'm not seeing a library for switches. That's a little surprising, seeing as they have so many switches, like symbols for switches. I guess switches also are a bit non-standardized. Every manufacturer makes a different style of switch, a different size, different shape. So they might have just looked at that and been like, so we might end up making that, or like looking for one for that too. The switches though, like I have a whole bunch of them. There's a specific, type that I got like a reel of a while ago. So, we might end up just making that too. Mounting hole. I'm just like quick looking to see if it's called something that's not a switch, because it is surprising to me that there's like no switch library at all. Like not under connectors, like they shouldn't be, but oh, here we go. Okay. So button switch keyboard, button switch surface mount, button switch through hole. So not really button switch. Button switches are usually like the momentary style that you like press and are clicky. Would it be under slide? Slide switches? No, there's no slide. Let's look at the button switch surface mount and just see what's going on there. Yeah. Of course, it's hard to get an idea of scale from this too, right? So, they have dip switches though, so we could at least do our, it's probably all through hole though. Oh, no, because we're in the surface mount switch library, right? Surface mount button switch library. It's interesting that they call that a button switch. I would not. Oh, there's slide switches in here too. Okay, I guess they called all of their switches button switches, whether or not they were buttons or slides or anything. I wonder if there are like toggles in here too. That's kind of weird. So yeah, that's a bit odd. But okay, cool. So this is like the giant switch library. All right, so we got dip, slide switch. Yep, that's kind of the style that we want. I haven't actually chosen a component here yet. This seems to be sort of like the biggest one, 2.454 millimeters. So it has a 10th inch pitch, which I think is kind of like what we want. So we will go over to our dip switch and assign it to our little pattern here. Excellent. So now let's see if they have any of our other kind of switches. So they're not dip switches. No push. Although it's weird. I guess they're calling dip switches slide switches, which yes, dip switches I guess are a type of slide switch. But what about, so they have single ones, but they're still like kind of that dip style. They're not like the bigger on-off style that we have. So let's see. Oh, hey, that's almost what we need, huh? Although we have three pins instead of 4. So, I think that's it. Nice. Awesome. So that one and that one. What was it? No, not that one. Cool. Hey. We will be double checking all of these footprints, by the way. All of them. And now I would be very surprised if they have our 4-pole dual throw switch. I feel like that's like a little bit specialty, especially in a surface mount version. But, let's see if they have anything that looks or is named somewhat similar. They really don't. They only have looks like they only have single pole, single throw switches like in this whole library. Is there another library that might have different pulls and throws of switches? Like all of them are labeled SPST. No. Which is like a little surprising. Yeah, a lot of styles of button switches, which is good. If you were just like using normal switches, it would probably be fine. But yeah, I'm just kind of checking through here randomly. Yeah, it's all labeled SPST. ISP meaning in system programming. Yeah, that's true. It could mean that too. I usually am more familiar with the acronym ICSP in circuit serial programming, but ISP, so I don't know if ISP is just like a abbreviation of that, in dash circuit maybe, but yeah, it could totally mean in system. That would make sense too. Those are button switch keyboard. No, those are all like Cherry MX switches. Cool. So yeah, I think we'll have to make one for that too. So we'll have to make one for our connectors and for our four pole switch. I'm going to apply save schematic. Apply save schematic and continue keeps us in there. Okay, cool. So I'm going to say okay. And I'm going to see if we can create a netlist now. Let's see if, yep, default format. That sounds good. See if it, make sure we're saving it in the right folder. Yep. Okay. And now I do believe we go to the, where did that go again? It's the other Kicad window. There we go. So now we're going to go to the layout. Yep. Maybe. It might take a little while since this is like the first time I have opened the PCB editor. Oh. Maybe it doesn't want to open. Maybe we should try it there. Or maybe there's a window somewhere that's hidden. Nope, that didn't. That seems fine. Strange.
What about,
that's that.
What about Kicad?
What's that?
What about Kicad?
Hang on a second. Let me get the right window back over there. Okay, so all right, there might be something about the process that I am missing, since this is the first time I've actually gone through it myself. Let's see. Oh, hey, there we go. Enable acceleration. There was our hidden window. Awesome. Yeah, we'll see how it likes streaming a bunch of video and doing Kicad and graphics acceleration. Let's do everything all at once. Cool. All right. So now we have our circuit board. This is just a, if you can see, you probably can't even see it because it's like in dark red on my screen. I'm just gonna make this big and zoom all. There's like a kind of a frame here in dark red, and it's just like a template frame as well. It's just for like if you're doing prints, if you're physically printing this out in, and we're like to submit it as documentation, then it has like that nice border around it and title block and all of that stuff. Like I hardly ever use that even when I'm printing out documentation, but we should probably do a nice Alpenglow one because that would be nice. So, all right, let's load a netlist. Netlist file. How about the one we just created? Okay, so a few errors that no footprints were defined. That's fine. I'm okay going forth with that. We know about that. There are a bunch of options here, and you might go back and forth between schematic a few times during the course of a layout, like we undoubtedly will when we make those other footprints. So like there are options to sort of like keep your existing footprints or reassociate everything, and that's helpful if you have a design that you're sort of in the middle of that you don't want it to touch anything that's already there. So yeah, I am assuming that I don't need update footprints checked like for the first time, that it would automatically do that, but I don't know. We'll keep it unchecked right now and just see what happens. Hey, there's everything. Look at that. Cool. So, whoa. What happened? Oh, weird. Okay, so it is attached to my cursor, but you can see like my cursor's way over there, so that when I went into the middle of the screen, I kind of lost all my parts. But so yeah, like this is actually like kind of like a relatively useful view maybe right now. All right, I'm just gonna place them there. So you can see all of the components. So my screen right now is just a little bit bigger. The screen space here is just a little bit bigger than a standard 8.5 by 11 sheet of paper. So you can see that like these are all of our footprints next to each other. It's a pretty small and compact spot. So everything is like relatively small. So, you know, when you're designing circuit boards, you spend most of your life zoomed in. So yeah, here we can actually see the physical representations of everything now, which is kind of exciting. And you can see the rat's nest, right? All of these like white lines that are kind of weird and going everywhere, they are showing me which paths should be connected to each other by copper. And then the names of the nets and the different connections are all written. These are all the pad numbers. So like when I zoom in, I can see like, oh, look, this resistor is connected to the red LED, and this side of the resistor, you know, needs to be connected to ground. These are all names that I gave them in the schematic. So when we go back to the schematic here, these are all of like these labels. So I've like named these nets. For nets that I have not named, because it's not important to name them all, that gets kind of like visually cluttered. Like, right, like this net is not named right here that connects the resistor to the LED. It is automatically like generated net names for those. So it's like net D3 pad 2, right? So yeah. And so what we're seeing in blue here will actually show up on like printed on the silk screen on the circuit board. So like this little half moon would show up. The things that are in gray or white are just for our reference. They don't actually show up on the circuit board. Everything in red right now is actually copper. These are the pads. These will be exposed. These are all the things that you solder to. And yeah, I think these, I don't know. I don't think, yeah, the big outlines here that you're seeing in white too, those are not going to show up. Those are just showing me like kind of the clearance area around that component that I should probably keep free of other stuff. If I move one of these components, and what I'll probably do is, I'm more concerned about the graphics looking right, so I'll keep those on the top layer. Probably we can do this now. All of these components, like just they kind of automatically import on the top layer. We're going to want them on the bottom layer because our you know, RBG graphic will be on the top layer. So are they all selected? I think they were all selected. Okay. I don't know how to just flip them. Yeah. Ooh, F, cool. I'm going to, do I have to pick them up first? I wonder, I don't know. So now I've just all flipped them to the other layer, and now I can rotate them all at once so that they're the same size up again. So interesting. So Kicad is using different default colors than I'm used to too. So I'm probably going to change all those around so that I don't have to like completely retrain my brain about what things are what. And yes, that might make it more difficult for other people who are used to Kicad defaults. So there is like a little bit of a trade-off there. I might think about that, but I probably, you know, so few people are going to open these files up in Kicad, even though I'm going to open source them, that I'm probably not going to worry about it. And I'm going to choose the colors that I want to choose. And besides, I think that is installation dependent. So my, like whoever is seeing the circuit board on their version of Kicad, I believe should see it in the colors that they have shown. But yeah, I'm used to blue being the bottom layer. I'm still used to red being the top layer. I set pink as the top silkscreen layer because it's associated with red in my mind. And then I choose a light blue to be the silkscreen on the bottom layer because it's associated with like the dark blue that is usually the bottom layer copper color. So I kind of keep things like that. But yeah, so in next week's stream, we will go through, I might work on this a little bit beforehand, but we'll go through like how I created like a board outline, and might go through how I like imported the graphics and placed everything and connected it. And I'll leave some of it unrouted. So I'll show you how to like connect them and like my methodology kind of for doing that. But yeah, exciting components. It's turning into a circuit board. Yee! Cool. So yeah, if you all have any questions, feel free to put them in the chat. I'll maybe shut up for a second and give you guys some time to type. Yay, Brittany, I'm glad you made it to the end. Awesome. I'm glad you liked it. I mean, I think that like circuit board design is cool and it's not incomprehensible, and like, I don't know, you like wonder how things are made, right? And what tools people used to make the things that they make. Like, I would love to see like an architect's program and like, how do they go about designing a house, right? Like, I think that that would be pretty cool. So, and I'm sure that there's like all sorts of software for things that you like don't even think about. Like, there's software specific to font design, you know, and I would love to see like a font designer go about designing a font. I mean, I think that that stuff is like super cool. But yeah, and there's like, of course, mechanical CAD is like a whole nother thing. And there are different styles of mechanical CAD to design like physical parts that are going to be, you know, machined, or are they going to be injection molded, or are they going to be like stamped or folded, or, you know, whatever. So cool. Awesome. Well, it is way past 7 p.m. and I'm going to call it. So yeah, hope you guys like learned something. Hope it wasn't too boring. This is definitely probably the most talking I've done in a live stream. And yeah, see you all next week when we'll do layout. Woo! Bye. Oh, yes, I have to confirm that I'm ending the broadcast. Still